Yeah, so we were looking at this problem. So this problem was we had the function y equals x squared, and we were rotating around the x-axis, and we looked for the radius of the rectangle, which is the curve, and it has to be a function of x. So the radius is the term in the parentheses. We square it because we have pi r squared, and we multiply by dx to get the width of the rectangle, and then we integrate this expression from the limits, which are the x limits, from 0 to 3. And I'm going to let you calculate that in a second. Now, the other case was looking at the red area, which was this same curve, but rotated around the y-axis. In that case, you had to take the equation y equals x squared and make it as a function of y instead of a function of x. So that's where we get the x equals the square root of y. And so because we're integrating with respect to y, we have to use the y limits, which is from 0 to 9. And the radius is the actual radius. So let me just draw that in there. So for the blue area, the radius is this. That's r of x. And for this one, the radius is this, and it's r of y. Okay, so that's the radius that we're rotating this element, a rectangle, around this curve. So go ahead and calculate these two things, just to give you some practice here. So you're going to multiply this out. You'll get x to the fourth. Here you'll just get y. And because they're polynomials, you only have to evaluate them at the upper limit, because the lower limit in this case is 0. If it wasn't 0, we'd have to evaluate it, but because we're going from 0. And the question is, which one's bigger? Because the blue one has a bigger radius, because it goes all the way out to a radius of 9. Whereas the red one only has a radius of 3, because it's just not drawn to scale. And just make it some number times pi. Don't put it as a decimal. Get my calculator out. They're actually they're a lot closer than you might think. I am going to make them decimals just so we can compare them. So for the blue area, you get, so we add 1 to the exponent, divide by the new exponent, plug in 3 and 0. When you plug in 0, you get 0. So 3 to the 5th is 243, so you get 243 pi over 5. And 243 divided by 5 is 48.6. And over here we get y squared. We add 1 to the exponent, divide by the new exponent, plug in 9 and 0, you get 81 over 2. And if you actually do the calculations, you get 40.5 here and 48.6, both times pi. So this one is a little bit bigger, but not a whole lot. Okay. Now this drawing is just to tell you the idea of what we're doing here when we're integrating with respect to x. That's the one on the top. So we've got the curve f of x, which defines the radius of the rectangle. The inside of the rectangle is on the x-axis right there. So all we're doing is we're stacking up these little thin rectangles and we're adding them together. So that's why the extent of the rectangles is our x limits, where the rectangles start and where the rectangles end. Whereas when you're rotating around the y-axis, you have horizontal rectangles. And the radius is the height of the rectangle, but the height this direction is x is a function of y instead of y is a function of x. So that's what this one was. So depending upon which axis we're rotating around, we may have to solve, if we're given y as a function of x, we have to solve it for x as a function of y. And we also have to change our limits because these rectangles are being stacked up in the y direction, so we have to add in the y direction. And the y values are the things that are the limits of integration. Okay, so we already talked about that. Talked about that. Yeah, well, okay, so we're just going to move to the next topic right now. Well, let me just show you what this is. I'm just going to mention this one. So what we have is, if you wanted to know the volume of a sphere, how would you do that? Well, if you look at this problem, and you can do it either way. You could do it around the x-axis or around the y-axis. This one's just I guess it's showing you how you would do it around the y-axis, but you get the same answer. But what you can think of is you've got this arc, which is defined by the function y equals the square root of 16 minus x squared. So that's the explicit version of the circle. It's the top part of the circle. You'd have to have minus the square root of 16 minus x squared to have the bottom half of the circle. So what you do is you rotate that around either the x or y, it doesn't matter, and that'll give you a half of a sphere. What we ought to do is do it instead of in terms of a given value of x, or given, here 16 is because the extent of the curve goes to 4, so you square 4. But you could kind of generalize it for some radius r. This would be r squared, and this would be from 0 to r. And then you could come up with the generalized formula for a sphere. But that's how you would figure out what the volume of a sphere is, by rotating that around the y-axis or x-axis and then doubling the value. So if you, in this case, as I said, we're rotating around the y-axis. So what you have to do in that case is, if you're given the relationship as y is a function of x, you have to then solve for it as x is a function of y. And because this thing's symmetric, they look pretty much the same because they are, except x and y are switched. So let's just write it out. If we rotated around x-axis, the volume would be equal to pi times the integral from x equals 0 to x equals 4, and r of y, the radius, if I drew this rectangle like that, the radius would be this function, which would be the square root of 16 minus x squared. So that's the radius, and then you square the radius, pi r squared times dx. If you'd wanted to do it around the y-axis, the way you'd formulate this thing is you'd say the volume is equal to pi times the integral from y equals 0 to y equals 4 of the square root of 16 minus y squared, quantity squared, times dy. Now, for anything that's not symmetric, something like y equals x squared, they don't look the same. It's just in this particular case they do. So, and the volume we would calculate would be, if we take this volume, so I could say if we double the volume, we get the volume of a sphere. In this case, a sphere with radius equal to 4. Well, let's go ahead and we'll go ahead and calculate it. So why don't you go ahead and integrate this thing? Give you a little practice here. So go ahead and integrate this one, which is pi times the integral from 0 to 4 of 16 minus y squared quantity dy. So you'll integrate this, and you'll integrate this. You'll evaluate it at the upper limit, subtract at the lower limit. We're going to get a number. We're going to double it, and then we'll compare it with the equation for the volume of a sphere to show you get the same answer. So the volume of a sphere is 4/3 pi r cubed. So go ahead and, well, the rest of it's down there. I'll let you practice again. So go ahead and so here's a comment about women's basketball. Hope I don't get in trouble for saying this. You know, watching it on TV, college basketball is well, you know, there's the there's you hear there was a movie called White Guys Can't Jump or something like that. Do you ever hear that movie? It was who was in that? It was he also was in that movie about zombies. No, it's not coming to me. Anyways, this movie was just about this white guy who was playing basketball, and I think that was the title. So, so women basketball players don't jump that well. It's just anatomically, I don't think it's possible. So it's always interesting watching because, you know, just in terms of when you get the ball inside and you get to shoot, they don't jump. It's a whole different concept. So what I think, this is my opinion, is what they need to do is develop a nice little short jump, not jump, a little hook shot, and they would dominate. Because when you get inside and you turn around to shoot, you're all at the same level, so it's easy to block, but it's hard to shoot inside. It gets all squished up inside. There's just too much. It's hard to get a shot off without somebody blocking your shot. And so so if you didn't have to turn around, if you just have a nice little jump hook shot, you'd be awesome. But anyway, I couldn't jump either, so that was my secret weapon. I'm coming from a position of knowledge as far as not being able to jump. So just a nice little jump hook shot, that would be awesome. So here I've integrated. Integral of 16 is 16y. Integral of y squared is y cubed over 3. Plug 4 in. And you get, oh, I've done that before. So that's the volume is 128 pi over 3. And if we, in this case, we double that. So if you double this volume, which is the area of a half sphere, or volume of a half sphere, you'd end up with 256 pi over 3. And the equation for the volume of a sphere is 4/3 times pi times the radius, which is 4 cubed. So that's really 4 to the 4th power. And so if you take, because I'm multiplying by 4 again, so if you take 4 to the 4th power, that's 256. So you get 256 pi over 3. So you see it does work. Okay, the next thing we're talking about is what's called the washer method. And what the washer method allows you to do is if you are rotating an area that doesn't fully extend to the x-axis, and it's kind of like calculating the area between curves, except it's different because it's volume and not area. So you don't just take the area but ultimately that's what you're doing. So what you have is you have two equations, one for rotating around the x-axis and one for rotating around the y-axis. So we use capital R to represent the outside radius and small r to represent the inside radius. So again, you have to plot the functions to know which curve is the outside function and which is the inside function. They also can't switch, so you'd have to, if you had functions that crossed over, you'd have to be careful about how you defined what the limits of integration are. And really what you're doing is you're taking the outside volume, that would be capital R of x squared, and you're subtracting the inside volume, which is small r of x, quantity squared, and the difference in those two is going to be the volume that remains. And if you're rotating around the y-axis, then you have to have the functions, both of the functions in terms of y instead of x, and you have to have the limits. The limits are in the y direction. So capital R sub y is the outside radius relative to the y-axis, and small r of y is the inside radius. And it's called the washer method because we look at the next slide. And I can't do the example because my program's not working. But if you take the same small width element, and instead of having it being solid all the way to the x-axis, in this case, you have just this outer part. Going to here is the outside radius. Going to here is the inside radius. So if I took the volume of the disk with capital R and subtracted the area of the volume of the disk with the small radius, then that leaves me with the radius, or this particular volume, the washer. And that looks like a washer, which if you've ever fooled with nuts and stuff like that, so that's what a washer looks like. Washers are used for when you have a bolted connection of some sort. A bolt is a rod with threads in it, and you want to tighten something down. Then these are used. They're used for spreading out the load when you take a nut and a bolt and you're tightening the nut down. You want, for two reasons. One is the nut is usually not circular, so it does tend to get stuck more so. But this also, what it does is it spreads the load out that between the nut and the thing you're trying to tighten it against. So that's the whole concept of washers. So all we're doing is we're going to stack all these little washers next to each other of different radius, add all those volumes up, and we get the total volume. So here's kind of like the example we did the other day, except instead of going all the way down to here and having a triangle, we're going to have a triangle, but the triangle is away from the x-axis. So you have to define what curve is the outside radius and what curve is the inside radius. So there's a few key things here that I have besides the function. This is the function y equals x, and that's going to define one surface, which is partially horizontal. It's diagonal. The vertical surfaces end up coming into play in terms of the limits of integration. Any horizontal surfaces have to be are associated with either the outside radius or the inside radius. In this case, it's the inside radius. So if I've drawn this rectangle to kind of just to help guide me in setting up the problem. So your rectangles are either horizontal or vertical. In this case, it's vertical. And because I stack these rectangles up side by side, and I can draw an arrow here, and that arrow is telling me that I need to integrate with respect to x. If the rectangle was the other way, this way, then I would have to integrate with respect to y. So the inside radius is the distance. It's always the distance from where you're rotating around. So this is r of y. That's small r of y. That's the inside radius. And then if you draw all the way up here, then that's the outside radius, which is, the different, it's changing. It's not always the same. Here it's the same. In this particular example, the outside radius is changing with respect to x. And I don't know why I put y in there. Sorry. Should have been x. So this is a function of x. This is a function of x. So let's just, knowing that I'm rotating around a horizontal axis, which I am in this case because I'm rotating around the x-axis, I know that I need to use this equation. So the things that I have to determine to be able to set up this equation is I need to know the equation for the outside radius, I need to know the equation for the inside radius, and I need to know the limits of integration. So the limits are either defined by a vertical line or they're defined by a point. If one of the sides, one of the limits of integration is defined by the intersection of two curves, then I just have to find the x-coordinate of that point. So in this case, A is going to be here. It's my leftmost part of my area, and B is the rightmost part of my area. And you can see that it goes from x equals 2, if I go down here, to x equals 5. So I can put those in there. I'll just write them out first. So A equals 2 and B equals 5 from this point and this line. Now the function that defines the outside radius is this curve, which as a function of x is just y equals x, so r of x is equal to x. And r of x for the inside is constant. It's just going to be equal to 2. So that's kind of like y equals 2. This is like y equals x. So, you might recognize them better in this form, but to fit them into the formula, we just have to give them the small r, the r, large R designation. So once we've done all that, then the rest of it's just usually a pretty easy integration. So we have pi times the integral from x equals 2 to x equals 5. Capital R of x is x, so I take x and I square that, and I subtract small r of x, which is just 2, and I square that, and then I multiply the whole thing by dx. And then I'm done for setting it up. So the rest of it is just evaluating the integral. So again, I'm going to let you practice on that. So integrate. Now in this case, you have to do both limits because it didn't go all the way, well, for two reasons. One is it didn't go to 0 here. That's the main reason. So you'll go ahead and multiply it out and then integrate. So go ahead and figure out what that is. I'll try not to get too far. Make sure you guys have a chance to work on that. Sorry for the first error. Is that what you guys got? Yeah. So yeah. Anyway, we add 1 to the exponent, divide by the new exponent. So we got x cubed over 3 minus 4x, and then we put in the upper limit, subtract the function at the lower limit, and 125 minus 8 is not 118, but 117, and this is divisible by 3, so we get that, and there's your answer. So it's not always a fraction, but anyway, that's how the washer method works. Let's look at this same problem, but let me just erase a few things here. Let's say I wanted you to rotate the same area around the y-axis. See if you can figure out how you would. So let me add a page. I'll write the equation that you need to have. So the equation for the volume rotating around the y-axis is pi times the integral from c to d of r of y, quantity squared minus small r of y, quantity squared, the whole thing times dy. So what we need to do is figure out what c is, what d is, what r of y is, and what small r of y is. So look over here. I've got the rectangle the wrong way, but just try to imagine rotating. I'll have to ungroup it. Let me not. So let me. Okay, so let me get rid of that. Get rid of that. Get rid of that. So what I'm going to do is I'm going to draw a rectangle this way. So if you drew a radius from here, what's the first thing you run into? It's this line. And then if you go to the other extent of the triangle, then you get to that. So I'll give you a couple minutes here to think about that, and then I'll ask some questions here. So I'm going to set it at 3 minutes. If you want to talk to your neighbor, that's fine. About this. 3 minutes. Start. And let me put this on one page so you can see it better. So it's a little bit bigger. You can see the numbers better. There you go. I saw in the paper where the biology teacher Allegheny is resigning, or did you see that? Do you know that?
He's joining the Coast Guard.
Is that what he's doing?
I'm not gonna hear it. Yeah, he's gonna join the Coast Guard and get his master's.
Oh, okay. Okay, cool. So he's leaving at the end of the year.
Yeah, he's only been here for 2 years though. Just quick turnaround.
Yeah, yeah, since Miss Bowling left. Okay, so Kelly, what is C equal to?
Is it 5?
Well, C is the limit, the y limit.
Oh, so 2.
2, yes. So C is the lower y limit. So you can see that in terms of the y direction, that this line y equals 2 is the limit. So that's correct. Okay, so Cray, what is D equal to? 5. And why is 5? Which point am I looking at? So here's 5, right? So that's right. It's that intersection. Okay, so I'll answer for you. So it's that part of the triangle. When we were integrating with respect to x, it was this intersection point, but for the y, it's the top part. Okay, who's next in line here? Maya. So what is capital R of y? So which one of those two lines is longer than the other? The top one or the bottom one? Yep. Okay. And what is that pointing to? It's pointing to this line, right? What's the equation for that line? 5. What equals 5? X, which is the same as R of y. Okay. So the answer is 5. Okay. So yes, that's the correct answer. Good job. Okay. So the outside radius, as you stack these rectangles next to each other and add up the areas associated with each rectangle rotating around the y-axis, the outside radius is always constant, so that's why it's 5. Okay, Mikhail, what is small r of y equal to? Don't say x, because that's not y. Right? What was your answer? Well, this is the inside radius. So that's not, you can see the inside radius is not constant. So it's got to be a function. So here is the function. Y is a function of x. So what if I rewrote that as x is a function of y, what would it be? X equals y. So the answer is y. Okay. So in the previous problem, when we had the outside radius was r of x, or y equals something, which is why we used x. So in this case, it's the inside radius that's what's varying. So now that we've defined all that stuff, the rest of it's a piece of cake. You just plug them into the formula. So C is 2, D is 5, capital R of y is 5. So you square that and you subtract the inside radius, which is y, and you square that, and then the whole thing is multiplied by dy, and then you'd integrate it again. Now, do you think the area, if I rotate this around the x-axis, I'll get some kind of volume, and if I rotate this same triangle around the y-axis, I'll get another a volume. Which one do you think is bigger? Do you think the volume rotated around the x-axis would be bigger, or the volume rotated around the y-axis would be bigger? This is going to be a voting, so you have to vote yes or no. Not answering is not an option. Okay, so we're going to ask you first if you think the volume rotating that triangle around the x-axis would be the biggest one, the bigger one. Okay? So how many people think if you rotate that triangle around the y-axis that it'll give you the larger area? Why is that? Daniel, you were pretty certain. What's that? Oh, you already did the numbers. Well, that would definitely be, that's one way of doing it. But if you hadn't done that, would you have known? Mm-hmm. I mean, if the formula was linear and not squared, it wouldn't matter. But because most of the triangle is in this part, because this is the wide part of the triangle. So you're going to have the wide part of the triangle rotated around the smaller radius. Whereas when you do it around this axis, the bigger part of the triangle is going to be at the larger radius. So that's the reason, just from a qualitative perspective. And it turns out that what did you get for the answer? 30. Well, oh, okay. 35.666 pi. And what do we get from the other one? I don't remember. 27 pi. Yeah. Okay, so I'm gonna officially assign the homework for this section now, even though we got a lot of stuff to go on. So you'll have something to work on after your test tomorrow. So, as far as section 2 is concerned, we presented all the formulas. The key thing is you've just got to be able to identify what the limits of integration are, what function defines the outside radius, what function defines the inside radius. If it's rotated around the x-axis, then you have to use in this case, you have to integrate with respect to x. If it's rotated around the y-axis, you have to integrate with respect to y. So it's the hard part is identifying what those quantities are. The integrations, for the most part, we deal with polynomials, so they end up being simple polynomial integrations. So that's the easy part. But people have trouble with it. So we're going to spend a lot of time trying to visualize what's going on. So I think we'll just stop there for today. We'll pick back up on Thursday. We'll see you tomorrow for the test. Remember, the front row goes to the physics lab.